Okay, so now that we have a sort of a general idea of what equilibrium is and how it is achieved, let's take a look now at how we can quantitatively explore this phenomenon. So we're going to take a look at the quantitative study of equilibrium. And this is all based on having a balanced chemical equation. So we've talked about the importance of balanced equations in the past. That was stressed a lot in General Chemistry 1. Okay, and this is another place where it is going to be really, really important. And the first thing that we're going to take a look at is something known as the reaction quotient. And that is abbreviated uppercase Q, subscript C, and the C here stands for concentration. And what this simply is, it's a relationship, it's a mathematical relationship of the concentration of the reactants to the product. So it relates the concentration of the products to the reactants. Okay, and the second part here is going to be important. In with the use of the balanced equation, specifically the stoichiometry. And the stoichiometry just means the coefficients that we use to balance the equation. So if we have a general equation written here, so you have A reacting with B, now we know what this special arrow means. It's reversible, meaning it's a equilibrium process that we're looking at. And then we have our lowercase letters. These are the coefficients, right? So the lowercase things, let's highlight these in yellow. Okay, those are your coefficients that we're concerned with here. We can write that reaction quotient as simply the concentration of the products raised to their whatever stoichiometric coefficient is, and then we're gonna divide it by now the same thing applied to the reactant. So the concentration of the reactants raised to their stoichiometric coefficient. In this case, we'll just say Y. So generally, right, QC, the reaction quotient, is equal to this relationship. If you have more than one reactant and more than one product, we're just going to multiply those concentrations by each other. This is also known as the law of mass action, right? When we write this this reaction quotient out. So in the example, right, so we have our A reacting with B to produce C and D. So the QC here is equal to the concentration of the product. So we have C raised to its coefficient from the balanced equation, which is lowercase c, times the concentration of the other product D raised to its coefficient lowercase d. And same thing for divided by the same thing for the reactants. Concentration of A raised to its coefficient A times the concentration of B raised to its coefficient B. So the more reactants and products you have, the more terms you're going to have in this reaction quotient expression. All right, and this is why having your balanced chemical equation is going to be really important, because we're actually using these coefficients in this expression. This is a way to quantify essentially how much products we have relative to reactants at a particular point in time. So let's take a look at one of these examples. Let's just pick one. We'll do the second to last one here. So the cadmium ion reacting with the bromide ion to produce this species here on the right side. So our QC expression, the reaction quotient, and again, this is the relationship for any point. We can write that for any point in the reaction process, at the beginning, in the middle, at the end, doesn't matter. So that'll be equal to, so our products here, our product is the cadmium. Then we have the Br4 with a 2 minus charge. So all of that goes in the square brackets. Our coefficient here, if you don't see a coefficient, the coefficient there is 1. So that becomes my power. And then that's the only product I have. So I have nothing to multiply by. Now divided by the reactant, so I have my cadmium ion, Cd2+. The coefficient for the cadmium here is 1. And then times the concentration of the other reactant, we have the bromide. So that's a Br minus. Okay, and then the coefficient there is 4. So it becomes to the 4th power. Okay, and that's all that it is. Now to simplify this, just like with your, when you see your coefficients in a balanced equation, we typically don't write the 1 in, it's understood to be there. Same thing for when you write the law of mass action, the reaction quotient. Okay, you don't need to put the 1 in as a superscript, that's understood if you don't see a number there. So we can just simplify it, and then we have our Br minus to the 4th power. So as long as we know what the concentrations of each of these species are, we can calculate this value for the reaction quotient at any point in the reaction process. So at any point in the reaction process, we can write the QC expression. Now, when we establish equilibrium, the point at which the point along the reaction process where equilibrium is established, we give that QC expression a different abbreviation, right? So when equilibrium is established, the QC expression actually becomes a different well, we call it a different expression, but the formulas is going to be the same. The formulas are going to be the same. We call it K, uppercase K, lowercase c, and that is known as the equilibrium constant expression. Okay, it's still, so the only difference here is we have that K, that uppercase K, as opposed to Q, and then the subscript C means, again, concentration. This is the special case of QC when equilibrium is established, right? So KC is still going to be equal to the concentration of the products, right, raised to their stoichiometric coefficients, divided by the reactants, raised to their stoichiometric coefficients. But this is going to be at equilibrium, right? So we call it the equilibrium expression or the equilibrium constant expression. And again, we can calculate these values for K at equilibrium or for Q at any point other than equilibrium. What we will see also is that the value for Q changes. Okay, so the normal reaction quotient value changes as time passes, and the reason why is because the concentration changes, or the concentrations change, especially here at the beginning, right? This entire part of the reaction that I'm highlighting, I'm shading in, right? This is not a flat line for the products or the reactants, right? It's a slope in both cases, so that there is a change in the concentration of each of these things. However, once we get to an equilibrium, which is right about these points here, then we have our flat lines, right? And at that point, the value for the reaction quotient doesn't change. That is the equilibrium constant, right? And that at that point, that Kc value is not going to change because the concentrations of the products are not changing, the concentrations of the reactants are not changing. So when we divide those, we're going to get a constant value as well, right? But at the beginning of the reaction process, as the concentrations are changing, the value for QC is going to change as well. It has to change because we're plugging in those values into that expression. All right, let's take a look at an example. It says carbonyl chloride, COCl2, which is also known as phosgene. That's this thing here. Used in World War I. It gives us the reaction, the equation, carbon monoxide and chlorine to produce phosgene. And then it says in an experiment at 74 degrees Celsius, the equilibrium concentrations. So now we have the concentration at equilibrium. So equilibrium concentrations of the following. We have CO, carbon monoxide, is 1.2 times 10 to the negative 2 molar. We're given the concentration of chlorine gas as 0.054 molar. And then the COCl2, the phosgene concentration is 0.14 molar. We need to write the equilibrium expression and determine the value of the equilibrium constant at 74 degrees. So the first thing here to keep in mind, and this may, you may see this in the problem and you may think, well, it has to do with something. The temperature is just something that we need to specify. Okay, so just like your reaction rates vary as a function of temperature, your equilibrium values can vary as a function of temperature as well. So we need to specify what temperature that is. Okay, because if we change the temperature, the equilibrium value, constant value may change as well. So we have all of the information provided. We have our balanced equation. So from this equation, we can write the expression for equilibrium, the equilibrium constant expression, the law of mass action, in other words. So we have the product, COCl2. Okay, its stoichiometric coefficient here is 1, so we don't need to put the 1 in, divided by the concentration of the carbon monoxide. Its coefficient is also 1 times the concentration of Cl2. Its coefficient is also 1. So everything is in a 1-to-1 mole ratio. We can just substitute our values now into this law of mass action expression. Okay, so at this point, all you're doing is you're doing calculator work. So COCl2 is 0.14 molar. We have our CO, which is 1.2 times 10 to the negative 2 molar. And we have our Cl2, which is 0.054 molar. And we substitute those into our calculator. And we end up with, what is that, 2.2 times 10 to the 2 as our value. Oftentimes, you will see the answer that you get for your Kc, your equilibrium constant value. A lot of times the unit is omitted because really what we're concerned with here is just the magnitude of the or the size of the Kc value is going to be the most important thing, or I'll say also, or the Qc value. Right, so the units are not super important in this case. It's how big is that number? Is it a really big number? Is it a really small number? Is it an intermediate number? Right, that's going to be what we're going to look at, especially as we get further into this section. So what about the magnitude of that equilibrium constant? Well, there are three general situations that can result when we calculate that equilibrium constant. So we can find, depending on the numbers you put in, you can get a very large value for Kc. Okay, so if you do get a large value for Kc, like this one shown here, what this suggests, right, is that this reaction will go essentially to completion. So all the way to the right, remember, to completion meaning from the reactant to the products. The products are on the right side by default. So if you get a large Kc, that means the product is favored. What we say then, the lingo that we use to describe this, we say is that the equilibrium lies to the right or that it favors products. Okay, so remember now, when we write that Kc expression, it is always products over reactants, right? So what this means is if the value for the products here, if this is large and this is small, all right, that means when we divide them, we're going to get a pretty big number. And what does that mean? Well, it means that we have a lot of products, right, at equilibrium, which means products are on the right. The equilibrium lies to the right, favors the products. So what constitutes a large Kc? Well, generally, we'll say large, right? And these are subjective things, but we can use some guidelines to help us. So generally, we can say a large value and a small value are as follows. So something that is greater than about 1 times 10 to the 2 right? That's 100. For the Kc would constitute a large value, meaning that equilibrium lies to the right, favors the products. A second outcome would be if we get a very small Kc value. Okay, so when we get a small Kc value, this would be less than something like 1 times 10 to the minus 2, or 0.001. Right? What we say is because it's small now, right, the equilibrium is going to lie not to the right, but lies to the left, or it favors now what's on the left side. It favors the reactants that are on the left. Okay, and again, I'm going to keep writing this. The Kc is products over reactants. Okay, so what will lead to a small value here for Kc is if the denominator is large and the numerator is small, right? So if we have a small numerator, that means we have small amount of products, but we have a large amount of reactants left over at equilibrium. That means that at equilibrium, we have way more reactants than we do products, hence it lies to the left. And we don't have a lot of products at equilibrium. The third possibility here is that the reaction will proceed to a significant degree, but not go to completion. And as a result, the equilibrium mixture then will contain comparable amounts of both reactants and products. Right, and that's the third possibility, and your Kc value there will lie somewhere between 1 times 10 to the negative 2 and 1 times 10 to the 2. So between 0.01 and 100, if you get that value for a Kc, we can say we'll have both reactants and products in the equilibrium mixture to appreciable extents.